Hello everyone. So today we'll be solving another random question. It's question number 73. So it's there on the blackboard. I will be reading on my laptop. So the question says that a nerve cell is in its resting state has a membrane potential of minus 70 millivolt, meaning that the potential inside the cell is 70 millivolt less than the potential outside due to a layer of negative charge on the inner surface of the cell wall and a layer of positive charge on the outer surface. This effectively makes the cell wall a charged capacitor. When the cell fires, sodium ions flood through the cell wall to briefly switch the membrane potential to positive 40 millivolt. Model the central body of the nerve cell, the soma, as a 50 micrometer diameter sphere with a 7.0 nanometer thick cell wall whose dielectric constant is 9.0. Because of cell's diameter is much larger than the wall thickness, it is reasonable to ignore the curvature of the cell and think of it as a parallel plate capacitor. So the question wants us to find how many sodium ions enter the cell as it fires. So first of all, let's record the data. So here we have data given. So first of all, we have the initial potential at the resting state, which was minus 70 millivolt. So initial potential, we can call it maybe V naught is equal to minus 70 millivolt, which is equal to minus 70 times 10 power negative 3 volts. But also, we have when the sodium ions start to enter the cell membrane, the inside of the cell membrane has the final potential of positive 40 millivolts. So you can say the final potential, we can call it just V is equals to 40 millivolt, which is equal to 40 times 10 power negative 3 volts. But another data is that the mode of the central body of the nerve cell, the soma, has the diameter of 50 micrometer. So the diameter, you have been given the diameter of the cell body, diameter, D is equals to 50 micrometer. So for this diameter, then the radius of the central body, the radius, I can call it R, is equals to 25. Times 10 power negative 6, it will be meter. But also another, that is the thickness of the cell wall, which was 7 nanometer. So the thickness, you can call it D, is equals to 7 nanometer. So it is 7 times 10 power negative 9 meter. So these are the main, also you have been given the dielectric constant K, which is equals to 9.0. So these are the main data for the question, and the question wants us to find the number of sodium ions that will enter the cell. Number of sodium ions. We can call this maybe E is equals to how much. So we need to find E. So in order to find the number of sodium ions, we know that we can consider the cell membrane as a capacitor because there is a layer of positive and negative charges and they're separated by a material between them, and that is what a capacitor is. So we can consider a cell membrane as a capacitor, and hence from the definition of a capacitor, from the formula to finding capacitance, from the formula for capacitance, we know that capacitance of a capacitor, maybe CO, is given by epsilon naught permittivity of a free space times a cross-sectional area A times distance of separation. But since the cell membrane is separated by a cell wall, it means there is a dielectric material. So the capacitance C will be given by taking the dielectric constant K, epsilon naught times cross-sectional area A divided by D. But for A, because we assume that the cell is a sphere, we can use the area of a sphere, which is 4 pi r square. So we can substitute this equation into the formula for capacitance. So capacitance K, C will be equals to K epsilon naught. Instead of area, you can write 4 pi r square divided by d. So it will be equal to K you have been given from the question, which is 9. So it will be 9.0 times, this one is 8.85 times 10 power negative 12. Then times 4 times pi times r is this one, 25 times 10 power negative 6. This is meter square, divided by thickness. You will take this one, 7 times 10 power negative 9. 7 times 10 power negative 9 meter. Square. So this one, after calculation, you get the value is 89 times 10 power negative 9, yeah? Power negative 12 Faraday, which is equal to 89 pico-Faraday. But also you know that capacitance C is equals to Q divided by change in potential, V. So from here, we can see that charge Q is equals to capacitance times change in voltage. So, but also you know that Q is equals to number of sodium ions times the charge, E. So we can say that number of sodium ions times charge, E, is equals to capacitance times change in potential. So from here, we can see that number of sodium ions is equals to capacitance times change in potential divided by the charge. So it will be equals to capacitance, we have already calculated it here, which is 89 times 10 power negative 12 Faradays times. But change in potential, you have to take the final potential, V minus the initial potential, V initial, divided by A. So it will be equals to, what was our final potential? It was 40. So 40 times 10 power negative 3 minus V initial, it was minus 70. Minus 70 times 10 power negative 3. This is V, divided by charge, it is 1.6 times 10 power negative 19. So if you calculate that one, you will get the number of sodium ions, it is 6.1 times 10 power 7. So therefore, you can conclude that the number of sodium ions that will influx or that will enter the cell is 6.1 times 10 power 7 ions. So basically, in the question, we have assumed that the cell membrane behaves as the capacitor. First of all, that was our first assumption. But also, we assumed that the structure of the cell is like a sphere. So that's why in the area, you use the area of the sphere. And from there, you can find the capacitance of the cell membrane. And after finding the capacitance, we can find the charge. And after finding the charge, you can find the number of sodium ions which we were required to find. So that's all about solving our question. Thank you.